Hello, and welcome to the Argyle AI/ML Technology Leadership Summit. My name is Nick Ciabatta with Argyle, and it's great to have everyone joining us today. A couple of notes before I turn things over to our esteemed speaker. First, a quick reminder to stop by our sponsors' virtual booths at any time during today's event and for the following week. Our partners are committed to providing you with valuable content and a great overall experience. At any time during today's event, you can visit their virtual booths from the main agenda page, which include complimentary materials, information, and meet and greet opportunities. To ask questions throughout the session, simply type into the Q&A chat, and we will address your questions at the end of the session. Now, without further delay, I would like to introduce our speaker, Swati Saxena, Aerospace Engineer, Technical Lead, NASA Ames Research Center. Welcome, Swati. Over to you.
Thank you so much, Nick, for the introduction. Well, thank you everyone for joining us this morning, afternoon, and I'm excited to share with you some of our work and vision in using AI and machine learning methods to accelerate digital transformation of national airspace system. And I'll be going over some real world examples of how we have utilized AI and machine learning methods over cloud and a combination of edge computing and on the cloud computing to deploy some of these predictive capabilities for field demonstrations. So before I go into the use cases, just to give you some background on what's our motivation behind this work. So the National Airspace System, which basically manages all the 40,000 plus commercial flights over the continental US every day, it's going through a digital transformation journey. And you can see really the four big buckets here, which the NAS is getting ready for. So, we would like to enable growth and integration of new operations. So new operations, by new operations, I mean new vehicles, new entrants such as electric vertical takeoff landing, eVTOL vehicles, air taxis, drones, delivery drones, and so on. So for that, we need advances in cybersecurity, automation of operations, and also establishing these communication standards so that we are able to manage this complex traffic that we are going to see in next 5, 10, 15 years in our airspace. Performance-based sustainable outcomes. So that's really, going or evolving from the legacy methods of making these decisions. We want to leverage more and more data, live data that's coming from the field to make these decisions and have these sustainable outcomes with higher accuracy. Fully integrated information environment where everybody has access to information related to flights, related to the weather conditions, related to the safety constraints, or any real-time changes that are happening in the environment, and then make a collaborative and informed decision based on that information. And then the last but not the least, interoperability in the NAS. So by interoperability, we really mean that we are able to build these agile systems and services which are able to connect with each other, build upon each other, and this will also enable better collaboration among different vendors, different service providers. So really all this is needed to enable this digital transformation journey of the NAS and get us ready for the growth that we are going to see in aviation operations in the next decade or so. So this is, if we look at the evolution chart of aerospace operations, this is how it would look. So if we break it down into 5 epochs, and today we are in the center where we are planning a trajectory of an aircraft to proactively and to maintain efficiency and also sustainability in the overall airspace operations. But this is where we are headed. So before we are ready for this highly automated environment, we are taking this intermediate step of building this collaborative environment where the tools can be built upon each other, and machine learning based prediction capabilities are a stepping stone towards this highly automated environment. And this is where you see this will act as an enabler for to get us to where we want to be in the next 10 to 20 years. So the current challenges, briefly speaking, we have the current flight data or weather data or aviation data in general is coming from different sources, as you can see, and it's often segmented and it has gaps. The current tools are more monolithic in nature, which means that they are kind of standalone tools with less flexibility of reusing them for different purposes or building complex services. Most of them are also deployed on premise, so they are on service providers' hardware, for example, and are not easily accessible across different sites, different air spaces, and so on. And then that also leads to very localized access and adaptation for that tool. So if a particular tool has been built to work, for example, in South Texas airspace, the Houston airspace, it needs to be modified quite a bit to be able to work in San Francisco airspace, for example. And using machine learning predictive methods helps scalability and adaptability of these tools across different sites. So what are the solutions we are proposing to address these challenges? So first of all, before we build a good machine learning predictive engine, we need good quality training data, as I think most of you would already be familiar with. So we are building an integrated aviation data stream called NASA Fuser, which integrates data coming from different sources such as FA, swim data, system-wide information management, airline data, airport data, vehicle, aircraft, weather, and so on, and then provides that standard and consistent data set for users to build their predictive services on. A microservices based architecture framework where an output of one service can be used as an input for another service, which helps in building these complex services or predictive tools for increasing operational efficiency. Cloud-based access. So this provides not only access to these services across the entire airspace, US airspace, but also provides easy adaptability of these services to other locations. By getting access to the good quality data, you are able to train your models on the cloud and then deploy them at newer sites. And this results into NAS-wide access with scalable solutions. So this entire framework that we have put together is called Digital Information Platform, DIP in short. And that's what when I say platform in this context, it would mean this cloud-based infrastructure which provides a platform to deploy these aviation tools and services via API gateway for all our users, for both the flight operator side and also to the air traffic control side. Okay, so with that background, I will spend some more time in explaining some of the features that this platform has and how we have implemented the machine learning workflow for predictive aviation services. I will briefly describe two use cases that we have looked at so far. There are many more, but in the interest of time, I'll highlight two, and then some summary, some key takeaways that I would like you to have from this talk. So this is a high-level design architecture of the platform that we are currently developing. As I mentioned, it's called DIP, Digital Information Platform, and it has all these elements that you see on this chart as currently available on the platform. So we have a catalog which lists the tools and services that people can search and discover and then register for. There is a security aspect. So we have authentication and authorization layer, which makes sure that all the users that get access to the platform have been authenticated. There is an API gateway via which users can register to the services, and the service providers can deploy their services onto the platform. Then there are some NASA developed services that are currently available on the platform, and part of those are the NASA Fuser service that I mentioned before, and then machine learning based predictive services, which I'll explain more in the next few slides. And then in the future, we will also have non-NASA developed services, which are mentioned as partner registered services on the platform as well. So currently, we also have an announcement for collaborative opportunities out via which service providers can respond to that ACO and can potentially become our partners on this project. Okay, so going a bit in more detail for the machine learning workflow that we have currently developed. So there is a training pipeline that is currently in place, and it's in the production environment. And we have used all open source libraries to implement this pipeline, so that it can be easily adapted and for our purpose, and can be easily built upon for other complex scenarios. So you can see the list of tools that have been used and the MLOps pipeline. And then we also have real-time and long-term machine learning performance monitors, because this is really, really important in our application, as how these machine learning models are performing over time. There could be a data like drift in the prediction because of some changes that are happening over time as the real-time data comes in. So we really need to be monitoring all those features, and these capabilities are eventually, or the outcomes are eventually going into making decisions for aircraft operations, which is so it's very, very critical to make sure they are all in line with the actual data that or the actual outcome that a controller or a flight operator would need in the field, and there's no error in making those decisions. So we start with historical data. There is a data query and data engineering stages where we look at the data, clean the data, and see if it's all making sense, there are no gaps, and so on. And then we do feature engineering, model fitting. We're using so this is a supervised learning model, and we're using XGBoost method to build this model. And then we have the model prediction. We are also collecting model metrics, its performance, and then ML flow storages is where it's all tracked and stored. Similarly, for the live prediction pipeline, there is live real-time Fuser data coming in. We do data query, data engineering, same steps, and then model prediction, and then this is the schedule building, which basically refers to the airport schedule that is being, that's one of the outputs of the um, prediction model here. And some of this has already open sourced in on GitHub, and there is a link here which you can go and have a look at. This is the overall data flow, how the data flows across the process, and without going into too much detail here, I would just highlight that we have both short-term and long-term data storage on the cloud, and there is also data coming in from weather sources, airport, and flight, and then it all goes to the long-term data storage, goes to building the ML model, and the steps that I showed on the previous slide are kind of highlighted here again. But just want to highlight that there is a version control that's there, and then the data also flows into the real time and long-term machine learning monitors. Okay, so the machine learning workflow that I just mentioned is used to implement all these machine learning prediction services that are currently available on the platform. Starting from the data, the training data that's coming in, the weather data, and then some other sources of data are used as an input for a tool called Airport Surface Model Orchestrator. So what it does, it basically uh, starts with a blueprint of the airport, and then it builds the model, the predictive model, machine learning based model for different what if applications. So configuration prediction, runway prediction, taxi time prediction, on time prediction. So these are all the prediction services that are currently machine learning based. So you get run these in parallel for a particular scenario, and then the output of all these services go into something called a terminal scheduler, NAS terminal scheduler. So that's where you set up your final algorithm or final outcome for setting up the schedule of the aircraft, uh, pushback time, takeoff time, and so on. So that's the schedule that's set up, and then uh, it also goes into this overall prediction service called CDDR, which stands for Collaborative Digital Departure Reroute, which basically uh, gives the flight operator an optimal path for the aircraft to take off. So there are on an airport, as you know, there are different runways that an aircraft can use, or departure gates and fixes that an aircraft can use to take off. So what happens is, if, for example, so a weather event or like convective weather builds up somewhere close to the airport, all the traffic gets rerouted to another through another gate, and that results into traffic congestion. And then you run into these delays, and I think all of you must have experienced this at some point of time, that your aircraft, you are in the aircraft, you have already boarded the flight, but then you end up sitting on the taxiway for almost an hour. So this kind of service tries to avoid that huge traffic congestion by effectively rerouting flights to other possible gates that are available at the airport, which are not part of the original flight plan, but through this continuous, prediction service running in the background. As they open up, the flight operator comes to know about those options, and then they can submit this reroute request. And once it gets approved, your flight can take off from a different gate, and that saves on to your overall delay time. And this is something that we have tested in real operational environment in Dallas Fort Worth International Airport, and also Dallas Love Field Airport, and have also collected real-time delay savings, fuel savings, emission savings, so resulting into real benefits across and cost savings for the flight operators. There is more information about about these services and what benefits they have realized so far. If needed, please feel free to reach out to me. Okay, so going into what's running under the hood, in the block diagram that I showed on the previous slide, this is just one example. So arrival runway prediction at DFW airport, before and after. So the improvement in the accuracy that you see, this is the traditional way of arrival runway prediction, and after using the machine learning approach, it showed improvement. We were actually targeting, even if it remains the same, that was kind of our target in the beginning, but we ended up showing a reasonable amount of improvement by using machine learning. So this is one of the tools currently being tested. The other use case that I would like to explain is the prediction of pushback time from your gate at US airports. So this is part of a university challenge that's currently live, and I have the link down at on the bottom of the slide there. The US university students are participating in this challenge, and the objective is to use federated learning approach to predict pushback time. And we would like to really see that if federated learning approach, where you have these local trained models for different with proprietary data for different airlines, and then you just use those models to build your own your overall predictive model without sharing the proprietary data. So that's currently going on, and this will also be a good use case for optimizing airspace operations using machine learning. So close to the end of my time, so I'll briefly talk about the key takeaways that we have found in this research work, especially related to machine learning. So the MLOps workflow is, once you have that in your test environment, it is really important to test it in the production environment, because that's when you run into different kind of challenges related to how much should you be splitting your work on the local computing, edge computing, and how much should it go to the cloud. What are the different bandwidth constraints or network constraints that you will run into when you are training your model. Training data has to be really good and meaningful, so a lot of emphasis is needed to develop good quality training data for these applications. And then the scalability and adaptability are very important, so specifically for aviation applications. Flexibility with the compute system, because of the nature of the training data, and also availability of the training data. Some of that data is on a machine which has to be connected via a VPN network or something like that. So a mix of a flexibility with the compute system is really important, and a mix of these resources have to be used. Federated learning can be a potential good use case for addressing some of the problems here. we have tested several machine learning methods and approaches such as supervised learning, reinforcement learning, and are now looking into federated learning. And there are very important applications of NLP as well that we are looking into, which I didn't have time to go into today, but in aviation. And of course, the domain expertise is really, really important. And in our case, field expertise is very important as well. So we continuously work with flight operators and controllers to make sure that the tools that we are building would actually be useful for them, and they continuously provide their input to us. So that's all I had for today. And here is my contact information, and also the link to the DIP project, and also the university challenge that's currently going on. So if you have any questions that we are not able to address today, please feel free to reach out to me. But I can take a few questions right now as well.
Oh,
Thank
great,
you.
Swati. Yeah, here's a question from the audience. Apart from machine learning algorithms, are there any applications that use generative AI in the NASA suite of tools and systems?
Yes, that's a good question, and we are looking into possible applications of generative AI. I would say it's still in the exploratory phase, and especially on to for the uh, the amount of data that we are collecting for communication between the controller and the pilot, or um, the pilot and the dispatcher on the ground. That's like one of the use cases where we are looking the potential use of generative AI to um, be able to better predict and help pilots with with making some real-time decisions.
Great. And here's another question. How can AI ML technologies be used to optimize fuel consumption and reduce carbon emissions in the aviation sector, contributing to sustainable operations and environmental conservation rather?
Yeah, yeah, absolutely. So the examples that I shared today are actually saving fuel, reducing emissions by optimizing these ground operations on the airport. So even if the so as you can see in this picture, the aircrafts are lined up, and when you are even sitting on the taxiway, you are burning almost 25 gallons of jet fuel per minute. So even if you can save a few minutes of your um, delay, you are making an impact on reducing emissions and reducing carbon footprint. So the examples that I presented today are actually making those contributions already, and we are also um, collecting all that data from the field. There are several other applications. uh, Maybe we will not have time to go into those today, but the ones I talked about are already making that impact.
Great. And I think we have time for one more question. Someone asked, we are struggling to determine if we even need edge computing. Do you have any advice for us?
Okay, so edge computing is, I would say, it's a quite, so one example I would give in the in the for the application that we are looking into. So the flight deck services, so flight deck tools, for example, you have this electronic flight bag, which is basically an iPad that the aircraft crew can carry in the along with them in the aircraft, and that has limited capacity, or the limited power, compute power. But there are certain scenarios. For example, you have the pilot observe some clean air turbulence or something, and then wants to do a quick uh, check on some alternate route that might be available to avoid that patch of turbulent weather, uh, and needs to run some quick calculation to identify that reroute. That's something that can be done on the edge relatively quickly, rather than uh, sending it back to the cloud, and it will take some time and to communicate back and forth as well. So I still think there are few cases, specific scenarios where edge computing is more efficient and is a viable solution.
Great. Thank you again, Swati, for such an incredible keynote. I also want to thank everyone else for joining us today, as well as our sponsor, Eightfold AI. This session, along with all of today's content, will be available on demand following the event. This officially concludes the Argyle AI/ML Technology Leadership Summit. Thank you again for joining us today and engaging in our content. Have a great day.